This is the brief on the invariance of tensor symmetry. So, tensors are these mathematical tools we use for things like stress or even space-time curvature. And this is all about a really core proof. It shows that if a tensor looks symmetric from one point of view, it's got to be symmetric from any other point of view. This means symmetry isn't just a fluke of how you're looking at it. It's a real intrinsic property of the tensor itself. Okay, so first up, what does symmetry even mean for a tensor? Well, think of a tensor as being symmetric if you can swap its indices, kind of like coordinates, and the component value stays exactly the same. So TAB is always equal to TBA. That's the premise we start with, this idea that the structure is inherently balanced. Second, how do we test this? We use the transformation mechanism. Basically, when you move from one coordinate system to another, the tensor's components change according to a specific rule. This rule uses partial derivatives to act like precise scaling factors, accounting for all the stretching and rotating between the two viewpoints. And finally, this all leads to the big payoff. Because we started with that symmetric tensor, when you apply those transformation rules, it doesn't matter how you change the coordinates, the math guarantees the symmetry is still there. And that's the whole point. It proves that symmetry is a built-in characteristic of the tensor itself, totally independent of how we choose to represent it. Tensor symmetry remains unchanged during coordinate transformations because it is a fundamental invariant characteristic of the tensor structure itself.